Okay, moving on to the next one. This one I found to be a little bit quicker. Most of it's going to be done right on the calculator, which is nice, and not as much, as work is setting up. Particle moves along the x-axis. Velocity is given by this thing. So make sure you're in radian mode, and we're on the interval 0 to 3.5. We have a position of x at -5 at time 0. Find the acceleration of the particle at time 3. All right, well, acceleration is the derivative of velocity. And this is just a Math 8 problem. You don't have to work hard. You're not using the quotient and chain rules to take the derivative of this thing. If you are, you're working way too hard. Okay, to find the acceleration at time 3, we're just going to, again, use Math 8. Okay, and we're going to get approximately -2.118 back. All right. And that's it. This is a 1-point problem. You don't need to write that you used Math 8 on the paper. The work that you see in front of you is all that you need to show for this. Okay, so that's that. Part B, find the position of the particle at time 3. All right, so they gave us velocity. They gave us a position at time 0. They want the position at time 3. This is very similar to what we did in the last problem. We gotta integrate velocity to get back to position. All right, but we're going to set up a bounded integral using the 2 time values in question here. In part B, specifically time 3, and then, in the setup of the problem, they told us the position at time 0. So we're going to use those as our bounds. So again, I'm setting up, a fundamental theorem of calculus setup here. I'm going to have a bounded integral that goes from 0 to 3 of our velocity function. And I know that that's going to give me the position function at time 3 minus the position function at time 0. And I'm just using x of t to denote position here. It's the x position at these time values. Okay, so very carefully on the calculator, we're going to punch in this integral. And I'm going to sub in -5 for the position at time 0. So watch that double negative. And let's see what we get when we integrate here. And I am getting 3.2397, so 240 to 3 places. All right. And if I now subtract the 5, position at time 3 ends up being -1.760. Okay. And they're given 3 points for that. 1 for the integral setup. Basically 2 for the integral setup, more or less. You get 1 just for writing that integral, and then you get a point for using the initial condition. So basically you want the whole thing set up like this so you can sub in the 5, and then 1 for the final answer here. Okay. All right, moving on to part C. Evaluate the integral from 0 to 3.5 of velocity and evaluate the integral from 0 to 3.5 of the absolute value of velocity. Interpret the meaning of each in the context of the problem. Okay, well, right away I can tell you that the difference between the two is that the integral of velocity is just going to be the total displacement, and we don't have any units, so no units to worry about there, but that's going to be the total displacement. On the interval 3, 5. And this one's going to be the total distance traveled on the interval 3, 5. Okay, so that's the difference between the two of those. On the actual exam, if you get a question like that, make sure you write nice complete sentences about it, okay? But that's that, and now really not too bad here because, again, it's calculator. All we got to do is punch both of these in carefully using Math 9. And let's see, doing the first one, we get about 2.844. And if we take the absolute value of velocity and integrate Here we're going to get 3.737. Okay, so, we ended up about 2.844 units to the right of where we began, but it took us 3.737 steps to get there. So we probably went a little past there and came back, something along those lines. Okay, and finally, part D. Let me make a little room here. Okay, for part D, a second particle moves along the x-axis. Position given by x2 of t equals t squared minus t on the same time interval. At what time t are the two particles moving with the same velocity? All right, so we have the given velocity up top here. All right, we'll call that velocity of particle 1. And we want to know, when is that going to equal the velocity of particle 2? All right, so let's figure out what the velocity of particle 2 is. That's not a bad derivative to take here. Okay, so the velocity of particle 2 would be 2t minus 1. So basically, our question is, when does the velocity of particle 1 up top equal this? Okay, well, this again would be something you're going to graph this in y1, you're going to graph this in y2. Check your interval. X min should be 0, X max should be 3.5 here. And just find where they intersect. And they intersect at about 1.571. And that's that. All right, 2 points for that problem, setting the derivative of x2 equal to velocity of particle 1, and then just coming up with that point of intersection. All right, folks, so plenty more to come. We'll see how this goes. All right, good luck.